Hi everybody, this is a video on L'Hopital's rule. Now make sure you pronounce it right. You don't pronounce the S in it. It's not hospital's rule. L'Hopital. Now this is a topic that used to be AB and BC. Then it was only BC. And starting this year, they added it back to AB again. Now when we do L'Hopital's rule, this is a good review of limits because L'Hopital's rule applies to limit problems. So we're going to go back to the beginning of the year. And before we add on L'Hopital's rule to the limit things we know, let's review the things that we know with limits. First of all, whenever we found limits, the very first way that we found limits was graphically. So you went to a graph, you used your one-sided limits, you made sure the one-sided limits were the same. If so, the limit existed. We also were able to find limits numerically, and doing it numerically, we made tables, and we chose values very, very close to the x value that we were approaching from either side. We did it algebraically. You could use complex fractions simplifying. You could use conjugates. You could cancel a common factor out if there's a hole in the function. Another way, we could do it symbolically, recognizing a formal definition of the derivative. These are the two formal definitions of the derivative. So you would look at what you were given. You would try using either of the two, pick out what f is and what a is, and then take the derivative of f at that a value. And the fifth way is L'Hopital's rule, which we're adding on today. So to make sure you remember all these methods first, I'm going to have you take a look at this problem right here in your notes. Now make sure you wrote all this stuff down. So if you didn't, pause the video now. So I'm going to give you this problem, limit as x approaches 4 of root x minus 2 over x minus 4. So you're going to do it all the 5 ways listed here. For the graph, go in your graphing calculator. If you don't have a graphing calculator, go to Desmos. And I want you to graph it up to 4 and a little bit past it. You only really need to go up to 1 here. Graph it, see if it approaches both things on either side. Now here, I want you to plug in these x values into x here and here and see what your y values are approaching. Notice if I try and do direct substitution, which is usually the first thing you're going to want to try. If I try plugging 4 in, I get root 4 minus 2 over 4 minus 4. 0 over 0. This is indeterminate form. So that means before what we would say is you have to try something different like graphically, a table, or doing some kind of algebraic manipulation. Today we're going to see how to do L'Hopital's rule to deal with this. But anyway, you can't plug 4 in directly, so that's why we're getting closer and closer to 4 from the left and from the right. So fill in this table here. Then I want you to do some algebraic manipulation. You could use factoring or complex conjugates. Just realize that when I say complex conjugate, I mean like x plus 2 and x plus 2. You could also factor the denominator, force it as a difference of 2 squares. Next, I want you to look at this formal definition of the derivative because this one looks very, very similar to the original. We don't want to use the h definition. That doesn't look similar to this. I want you to pick out what f is by comparing this to this, pick out what a is, and then realize that what they're really asking for is the derivative of f at a. So all of these should have the same answer at the end, and you should be getting a limit of 1/4. So if you didn't get 1/4 for all of these, go back and check it. The last way we're going to come back to this slide is do L'Hopital's rule with it. So that's the one I will do with you. So let's figure out what L'Hopital's rule says. Now there is a proof for this. We're not going to do the proof. I'm just going to tell you what it is. There are proofs out there though. So first of all, f and g have to be differentiable. So the theorem says if I have two functions that are differentiable, and the limit as I approach some x value for f is 0, and the limit as I approach that same x value for g, if both those limits are 0, then if I try and do the limit of f over g, I would end up with 0 over 0, the indeterminate form. So what you can do instead is do that same exact limit, but do the derivative of f over the derivative of g. This limit will be the exact same as that limit, and this is the one that would work with L'Hopital's rule. The same thing applies if I have differentiable functions, this time if the limit for f and the limit for g are infinity. So if I were to do the limit as x approaches a of f over g, I would end up this time with infinity over infinity. Doesn't work, it's indeterminate form as well. What you can do is take the derivative of f, the derivative of g, and try again. So this method, it's important that you realize it's used to find limits of indeterminate forms 0 over 0 and infinity over infinity only. Right here, now that you know what L'Hopital's rule says, the danger is you don't want to just run to every limit and apply L'Hopital's rule to it, because sometimes you'll get the wrong answer if you do that. Only apply the rule if you can and if you need to. First of all, f and g need to be differentiable. If they're not differentiable, don't even try it. Second of all, you need to actually end up with the indeterminate forms. Sometimes when you try direct substitution, you'll get a limit that works. So if you're not getting an indeterminate form, don't try to use L'Hopital's rule. One thing to keep in mind is for the more advanced L'Hopital rule problems, you'll have to apply it more than once. So you'll take a derivative, try again, you'll still end up with 0 over 0 or infinity over infinity, and then you'll have to do L'Hopital's rule again. Sometimes you have to do it 3 or 4 times. Another thing to realize is sometimes when you try direct substitution, because you should still always try direct substitution first, you'll end up with weird indeterminate forms like these. There's 1, 2, 3, 4, 5 different ones. You need to transform these into 0 over 0 or infinity over infinity before you even try using L'Hopital's rule. What you'll do for these 3 here is you'll just use basic algebraic simplification or rewriting things without negative exponents. What you will do, fix this, I only meant to underline the first 2 for algebra. What you'll do for these 3 is you'll use logarithms. Those are the most advanced types. Whenever you have to use logarithms to rewrite it into one of the familiar indeterminate forms. Now that we know what L'Hopital's rule is, let's go back to the first one here. Now you should have already done these out using all 4 methods. If not, do that quick and pause the video. All right, so L'Hopital's rule. First of all, if I try and do direct substitution, let me write the problem again here. Limit as x approaches 4 of root x minus 2 over x minus 4. If I do direct substitution, again, I got 0 over 0. So what I'm going to do is I'm going to apply L'Hopital's rule, and you do not have to put LH over the equal sign at the point when you're doing L'Hopital's rule. I just usually do just to make my work clear and indicate to you when I'm doing it. This is my f, this is my g. If you get 0 over 0, you should be able to do the derivative of the top over the derivative of the bottom and try again. So the derivative of x is 1/2 x to the negative 1/2. Derivative of a constant is 0, all over 1 minus 0. Let's clean this up before we try direct substitution again. All right, and let's see if it works now. Now you can do direct substitution, and it works. 1 over 2 times 2, 1/4. And that agrees with what you should have gotten for all of these. So L'Hopital's rule is pretty simple. Some of the problems are really easy. Like I said, some can get more complicated. You just always need to make sure that you're checking that you actually need to use it, and you're not just using it for random problems that don't need it. Let's try 2 other problems quick, just so when you come in tomorrow, you're able to do more difficult problems. Okay, e to the x minus quantity 1 minus x over x. I'm approaching 0. I'm going to do direct substitution to make sure that I even need to apply L'Hopital's rule. 1 minus 0 over 0. E to the 0 is 1 minus 1 over 0. Okay, so I'm definitely going to need L'Hopital's rule. I'm going to rewrite the problem with the negative distributed. And now I'm going to go ahead and apply L'Hopital's rule at this point here. So I have the limit as x goes to 0. Derivative of e to the x is e to the x. Constant is 0 plus 1 over 1. Let's now try direct substitution. E to the 0 plus 1 over 1. 1 plus 1 over 1 is 2. So after applying L'Hopital's rule right here, that made the limit work. It's not an indeterminate form anymore. Here's another one. X can approach anything. It doesn't have to approach 0 or a number. It could even approach infinity. For these, you're going to have to just think about what the function would be doing if x went to infinity. So let's try direct substitution. It's going to seem a little weird plugging in infinity. So I have infinity times e to the negative infinity. So let's think about what e to the negative x would look like. Scratch that. You could think about the graph, but another way to think about it is this. If I have e to the x and I plug in numbers for my exponent, if I plug bigger and bigger numbers in for x, I'm going to have a bigger and bigger output. This is saying what would realistically happen if you plugged in smaller and smaller and smaller numbers, like -10, -100, -1,000. This quantity is going to approach 0. So you need to be thinking about the numbers like that and seeing what would it really be. So right now I have 0 times infinity. Now this does not look like one of the indeterminate forms that we need to even apply L'Hopital's rule. It has to be one of these two. So let's look at our original function and see if we could rewrite this. And if you think about putting this in the denominator to get rid of the negative exponent, now let's try plugging in infinity over e to the infinity. Infinity over, so if you take e and you plug in bigger and bigger and bigger numbers, this is really just going to be infinity. Okay, so now I have an indeterminate form that I can use L'Hopital's rule with. So let's go ahead and apply L'Hopital's rule with it. So let's take, notice I'm still writing LIM every time, derivative of the top over derivative of the bottom. And now let's try direct substitution. We already established that e to the infinity is actually going to be infinity. 1 divided by infinity. Again, before, if you were in Algebra 2, you would have looked at this and said, what the heck is that? It doesn't work. Think about taking 1 and dividing it by bigger and bigger and bigger numbers. What your output will eventually approach is 0. So you're allowed to take something like 1 over infinity and say, okay, it's actually going to be 0 in the end. All right, so in class, we're going to try some more difficult problems. We'll practice deciding when we need L'Hopital's rule and when we don't. So make sure you have these 2 slides down. Make sure you've actually done this problem out all 5 ways, and I will see you tomorrow.